Hello, welcome to the first video introducing Year 13, the second year of the A-Level Maths course, otherwise known as A2. So you might be wondering why this is headed up as Chapter 0.1. So Chapter 0.1 as in a sub-chapter of Chapter 0. Why Chapter 0? Why not Chapter 1? Well, Chapter 1 of the Edexcel book just gets straight down to business. It jumps straight into proof by contradiction. And I was thinking, after a long summer, it might be worth, especially given the leap in difficulty from Year 12 to Year 13, giving a bit more groundwork and background to what is introduced in Chapter 1 in the Edexcel course. So Chapter 0 is an introductory chapter to ease you into Year 13 and give you a richer understanding of some of the concepts needed to get your head fully around the idea of proof in Chapter 1. So Chapter 0 is a mixture of two sub-chapters which are purely introductory, and also the first bit of Chapter 1 in the Edexcel course book for Year 13 Pure. So this is going to be almost like storytelling, really. If you have notes in front of you, you could just read them through. I'm going to explain the slides in front of you, and at the end there's going to be a few questions to try, just to make sure you understand the concepts. If you're of the keen type, want to just jump straight to trying them, feel free to skip to the questions and then skip back if you need to understand some parts of the video in order to answer the questions you're not sure about. So anyway, let's have a look at this to begin with. Let's talk about our current number systems. Importantly, a very obvious question: what actually is a number? Well, people of all ages can answer this question to their own satisfaction and within their own frame of reference. So the below definition has just been pulled from the Oxford English Dictionary. So a number is just a mathematical object used to count, measure, and label. It's been shown that bones and other artifacts have been discovered with marks cut into them that many believe are tally marks. These tally marks may have been used for counting elapsed time, such as numbers of days, lunar cycles, or keeping records of quantities, such as of animals or livestock. In modern mathematics, each category of number can be represented as a set, which is a collection of distinct objects which are called elements. The infinite set of numbers, sufficient for counting, 1, 2, 3, 4, 5, that set is known as the natural numbers, and it's represented by the symbol n, which is double-struck. So it's a fancy-looking n capitalled, which just stands for natural number set. So algebraically, it can be thought of as this. So n is a set beginning with 1, then 2, 3, 4. Then algebraically, n minus 1, 1 bigger than n minus 1 is n, 1 bigger than n is n plus 1, then dot dot dot, just to denote that it goes on forever. It is an infinite set. And as mentioned before, those are some references for you. So at the bottom, that's where it's pulled from, Oxford Online Dictionary. So, a bit more background. So, properties and notation. So, 3en. What does that mean? Well, this means that 3 is an element of the natural numbers. So that fancy looking E symbol stands for is an element of. In plain English, it just means 3 is a natural number. 7,984. This doesn't mean 7,984. The comma is a separator separating two different elements. So this means that both 7 and 984 are elements of the natural numbers. Minus 3 with an E with a line struck through, then an N. This just simply means that minus 3 is not an element of the natural numbers. Natural numbers are non-negative, starting at 1. So minus 3 is not a natural number. Minus 3 is known as an integer. We'll mention this later. Algebraically, m, n, e, n. Looking at this one here, it's very similar to this, but just in an algebraic sense. So this here means that both m and n are elements of the natural numbers. M plus n That means m plus n, whatever that ends up being, is an element of the natural numbers. And finally, mn is a member of the natural numbers. mn is a product of m and n. So that's just saying there that m times n is an element of the natural numbers as well. There's also a concept which is very important called closure. So closure, if m and n are members of the natural numbers, then m added to n will also be a natural number. So this idea is just saying that if we add two natural numbers together, the result will also always be a natural number. That's what we mean when we say that the natural numbers are closed under addition. It just means a natural number added to a natural number will always give a natural number. So, in other words, the natural numbers are closed under addition. Now, we can think of multiplication as repeated addition. So consequently, the natural numbers are also closed under multiplication, because you can always think of m multiplied by n as m added to m added to m added to itself n times. And so the product of two natural numbers will also always be a natural number. And so we have addition and multiplication, which are closed. If we take two natural numbers and either add them together or multiply them, the result will either be a natural number respectively. Can we think of cases where an operation is not going to be closed under the natural numbers? For example, subtraction. Will one natural number subtract another natural number always give you a natural number, or is that maybe not closed? Well, if we take, for example, 4 subtract 9, 4 minus 9 would be minus 5, and minus 5 is not a natural number, and so subtraction is not closed under the natural numbers. How about some applications of the natural numbers? So the main operations, the main applications, we've got 5 here to discuss. So the most obvious one, going back many, many thousands of years, is going to be counting. So there's one duck, another one, that's 2, another one gives us 3, another one comes along, that would be 4. But so far I have 3 ducks. 3 is an element of the natural numbers. So we can think of counting as just moving along the succession of natural numbers consecutively. Addition. So if you have 3 ducks, I'll group these together like so in this blue ring. Then imagine another one comes along. We'll colour that green to just distinguish it. Then we have 3 ducks which we initially had, and another one comes along, then we can say that we have 3 ducks initially plus an extra one which is 4. That's also a natural number. Opposite of addition is subtraction. So let's imagine we start off with 4 ducks, but then 1 duck leaves us. Sorry, I mean to say 1 duck remains. So if 3 ducks leave, that leaves us with just 1 duck left. 4 minus 3 equals 1, and 1 is an element of the natural numbers. Multiplication. So 2 ducks, circle those and group them together. Imagine we have that grouping doubled. So 2 multiplied by 2, that gives in total 4 ducks. So 2 multiplied by 2 is 4, which is also a natural number. And the final one we're going to discuss now is division. So if you've got 4 ducks in total, these can be paired into 2 groups of 2. So if we take 4 ducks and divide them into 2 equal groups, that gives us 2. In other words, 4 divided by 2 equals 2, which in this case is also an element of the natural numbers. So you should know by now, though, from earlier maths, that addition, subtraction, multiplication and division are grouped together and known as arithmetic. Just a little note for you though. Counting, like I've mentioned before, it could be interpreted and thought of as a special case of addition, whereby each object to be counted is assigned the number 1 and then just counted through addition. So in other words, like 1 plus 1 plus 1 plus 1 would be 4. Or in terms of our ducks, 1 duck plus another duck plus another duck we can think of as being 1 plus 1 plus 1. And of course, 1 plus 1 plus 1 equals 3. Now, of course, there are some limitations of the natural numbers. For example, we know and are familiar with already the negative numbers. Negative numbers aren't included within the set of natural numbers. So this would have been something which wouldn't have been pondered at a certain point in human history. Obviously, since you've been born and much before that, it has been, so it seems very natural to us. But at some point in history, people would have realised the natural numbers have a limitation, which led to the number system having to be extended out of necessity. So, on that note, let's just consider the shortcomings of the natural numbers. Can you think of any examples whereby counting, subtracting, or dividing natural numbers would not produce another natural number? We're going to omit adding and multiplying from this question, since we've already established that the natural numbers is closed under both addition and multiplication. Well, what if we wanted to count, for example, the number of items inside an empty box? So counting. 0. 0 is a concept which had to be actually set in stone. The idea of 0 wasn't always obvious as it is to us now. So 0 isn't a natural number, but of course having no items is a very real idea which needed to be, and needs to be obviously, discussed and solidified. The natural numbers don't suffice for that, however, because 0 isn't a natural number. So that's a limitation of the natural numbers. How about subtraction? Well, if we're subtracting a number which is bigger than our starting number, that won't give us a natural number. For example, 3 minus 4 is negative 1, and negative 1 is not a natural number. So there's another limitation. And of course, division, if we take 1 and divide it into 2, we're going to get a half. So a half is not a member of the natural numbers. So fractions aren't always going to be natural numbers. In fact, almost all the time, fractions are not natural numbers. The only way a fraction could be a natural number is if the denominator exactly divides the numerator. So how do we resolve these shortcomings? The examples above suggest that the natural numbers are insufficient for counting the number of objects in an empty box, the concept of 0, subtracting a larger number from a smaller natural number, and dividing quantities into fragments. So this idea of fraction actually comes from this word fragment. And fragment, it's a late Middle English word from French, which initially comes from Latin fragmentum, or frangere, which was to break. So fraction has the same Latin origin, fractio, which means breaking, as in, for example, to break bread. So 0, integers, and rational numbers, just like I've discussed on the other page. Integers, in terms of negative looking whole numbers, and rationals, which we're going to see in a moment, are like fractions. So to ensure that we can answer questions such as 3 minus 4 and 1 divided by 2, we've been forced in history to extend the number system. So let's introduce 0. So if we define a new set of natural numbers to include 0, essentially we can adapt the set of natural numbers to have 0 at the start of it. And so that has the symbol n subscript 0. The subscript 0 just means the natural numbers with 0 included, which you can see here in red. So that now helps us to have the difficulty resolved of this concept of counting items in an empty box. So 0 has now been defined into existence, if you like. It's worth noting that while the use of numerals, in other words numbers, including place value, dates back at least 5,000 years, scholars in Europe were still debating whether 0, which represents nothing, could be a number as recently as 500 years ago. So inventing zero, solidifying the concept of it, hasn't been as straightforward as what you might imagine. So I'm going to put a link at the bottom for some more history about the history of zero. So here it is now, if you're interested. So another thing to introduce is integers. So the set of integers consists of 0, in the middle if you like, the positive natural numbers, also called whole numbers or counting numbers, and their additive inverses, which you might know just simply negative numbers. For negative integers, -1, -2, -3, and counting back towards infinity, negative infinity. The blackboard bold Z stands for the German word Zahlen, meaning numbers. So the symbol looks like follows, and what will follow next will be the set denoting all the integers. So this is the double struck Z symbol, and as you can see it starts with this ellipsis ... and this just denotes that there's an infinite number of integers which are negative. So for example, this can't start at any particular number. We could go lower than -1 billion. So this ... just represents all the infinite negative integers before -4. Then above -4 we have -3, -2, -1, 0, which is the dividing point between the positive integers on the right and the negative ones on the left. Then of course you have 1, 2, 3, 4, then ... on this side, denoting that the integers go up towards positive infinity as well as starting down here towards negative infinity. So the ... means we can't put any upper or lower limits on the integers. They are an infinite set. So next, need to mention something about inverse elements. So the definition from before labels the negative branch of integers as the additive inverses of the counting numbers. We can think of subtraction as the addition of two integers, making, in a sense, subtraction a non-essential arithmetic operation. So just to take an example, we could think about 9 minus 13, where 9 and 13 are natural numbers. We can think of this instead as 9 added to the negative integer, negative 13. So 9 added to negative 13 would give us -4, which is the same result as if we were to do 9 subtract the positive natural number 13. So in this way we can see that the addition is closed using the integers. Okay, so addition is closed including the integers, and indeed subtraction is closed under the integers, but isn't closed under the natural numbers like we discussed before. So the integer negative 13, it's the inverse of positive 13. And why is that? Well, it's because positive 13 added to its inverse gets us back to 0. So every integer has an inverse such that the number added to its inverse gives 0. For example, +5 has an inverse -5. The inverse of -7 is +7, and so on. We're actually already working within the structure and using the rules which define the arithmetic involved in adding integers. This is an example of something called a mathematical structure, which is a group. So next up, another way we could explain the evolution of thinking that extends ideas of counting and addition is to say that if we wanted to be able to solve all equations of the form a plus x equals b, where a and b are known and x is unknown, for all such equations to have solutions, we'd need to work in the set of integers. For example, 9 plus x equaling 5 has no solution within the set of counting numbers, has no solution within the natural numbers, because the solution here would be x equal to -4 or -4, which is an integer. And so integers give us more freedom and more scope, and integers are closed not just within addition and multiplication, but now are also closed under subtraction too. So next we need to think about representations and partitions of the natural numbers and integers. In order to work with whole numbers, by that I mean the natural numbers and integers, in a more generalized way, we need to be comfortable with representing these numbers in ways that demonstrate particular properties. For instance, we might want to create partitions or subsets to allow us to focus on numbers with specific properties, and this is very useful when it comes to proving certain properties of numbers, or proof questions indeed for your A-level exam. So a common useful ploy is to partition the number line into the even numbers. So it should be obvious that the even numbers are a subset of both the natural numbers and the integers, depending, that is, on whether negative numbers are to be taken into consideration. Some people might just think of even numbers as positive only. In fact, that's my preference too. Anyway, if we just think about going for the positives, then the set of even natural numbers can be represented as follows. So we could have 2, 4, 6, 8, 10, all the ones in the 2 times table essentially. That's doing it purely numerically. Or, invoking some algebra, we could say 2, 4, 6, 8, 10, then ... to denote a unspecified period of extra values in there until we get to 2n, where n is some natural number, and then after 2n ... which just denotes that the sequence of multiples of 2 goes on forever. Or we could denote it via set notation like so. We can write 2n, then colon, n is a member of the natural numbers. So this is read in terms of 2n such that, or so that, n is an element of the natural numbers. So 2 multiplied by n will always generate an even number so long as n is a natural number itself. So just to say again what I've explained, 2n colon small n e big double struck n just means the set of all elements 2n such that n is an element of the natural numbers. So we can also think of these sets as sequences whereby 2n is just the nth term rule for the even natural numbers. So going back to the nth term rule from GCSE, we can even illustrate it in a table like the one below. So looking at this here, we'd have the following. So n goes 1, 2, 3, 4, and 2n is just double n in all cases. However, odd natural numbers can be represented in a similar way. So if you just imagine the nth term for any odd number, it would be 2n subtract 1. So 2n is the evens, but odd numbers start 1 lower. So if we go up in caps of 2, hence 2n, but the first odd natural number is 1 lower, hence minus 1. It's 1 lower than the first natural even number. 1 is 1 lower than 2. As another example, we might want to combine evens and odds, which will reconstruct the natural numbers as follows. So in red, we've got the evens, and in blue, we've got the odds. So this is particularly powerful when considering a proof by cases. So a proof question might be, for example, of a type, show that a certain property is always going to end up being odd for any natural number. That could be a question where we could say, well, let the first number be even, so represent it by 2n, or let it be an odd, and represent it by 2n minus 1. So a proof question which sets out a proof for a natural number could be sometimes easily solved by considering the natural number as either the case where it's an even natural or an odd natural number. And if you can prove it to be true for both those cases, we've proven it to be always true, and we'll solve the proof because any natural number is, of course, always even, or if not even, it's odd. Similarly, the integers can be expressed in different multiples. So considering even as being multiples of 2, we could express them in terms of multiples of 3, or indeed 4, 5, 6, and so on. So if integers expressed as multiples of 3, first of all, what we'd need to do is to consider the nth term rule for multiples of 3. So in other words, it'd be 3, 6, 9, 12, 15. The nth term there is 3n. Again, that'll give you an infinite set of multiples of 3, and also within there there'll be non-multiples of 3. So you can think of every third number in the 3 times table as being a multiple of 3. So let's have a look here in terms of on the number line. So these are all representing consecutive numbers. So 3n minus 1, 3n minus 2, 3n minus 1, 3n. So in red, we've got the multiples of 3. In blue are non-multiples of 3. So partitioning the number line like this case would be useful, for example, if we had a proof question which involved prove that something other is always a multiple of 3, or proving that if n is a natural number and it is a multiple of 3, a certain result holds. We could prove it by cases, considering the cases where n is a multiple of 3 like so, or a non-multiple of 3 like these 2 other representatives here, for example. So, extending representation as multiples or sequences to the integers, so not just for the naturals. Suppose we wanted to represent the following infinite sequence of integers in a generalized form. So not just 159, but how about the 4 times table, or this would be the 4n minus 3 sequence, extending it back into the negative numbers. So how would we include integers for the sequence 4n minus 3? Well, first of all, we'd find the nth term rule for the sequence. So let's imagine the sequence were 4n minus 11. Okay, so this may well be 4n minus 11 here. So for example, if n were 3, that'd give us 1, and if n were 4, that would give us 5, and so on. So this indeed would also work. So 4n minus 3 would be one way of representing this sequence. Another way would be 4n minus 11. So we can then write that sequence as a subset of the integers. So this would be 4n minus 11, such that n is an element of the integers. So a fifth example. How about the set of all cubic numbers? That also will be a subset of the integers. The cubic numbers are whole numbers that can be both positive and negative. So like I've said, it does make them a subset of integers because a cube number can be a negative. So it can be represented as follows. So a cubic number is any integer cubed, so we can write it as n cubed such that n is any integer value. Now, rational numbers. So we've gone from the natural numbers, which were only closed under the operations of addition and multiplication. That didn't have closure for subtraction or division. So then we thought, well, the integers open up more possibilities because the integers are closed under subtraction, but are the integers closed under division? Well, this is where the rational numbers come in. So we've discovered that 1 divided by 2, it wasn't possible within the set of natural numbers. It's also not possible with the integers either. 1 divided by 2 isn't going to be either a natural number or integer. So division still isn't closed under the integers. So we still have a problem to resolve. So having extended the natural numbers to include 0 and negative whole numbers, we still can't answer the question, but, well, what is 1 divided by 2? So the answer can't be 0, because something will still exist when we divide 1 into 2 equal parts. But nor can the answer be 1 or some other integer, as we're dividing it by a whole number. So therefore the answer must lie between 0 and 1. It's got to be less than 1, because you're splitting it into something smaller, but it's got to be greater than 0, because if you split a whole into 2 parts, each part has to have a size and can't be of 0 size. If we set out the integers on a line, there would be gaps in between them, obviously, with many more numbers, which wouldn't be integers, falling within these gaps. So for example, between 0 and 1, we'd find the numbers a half, 3/4, and 2/5, and so on and so forth. In fact, there'd be an infinite number of these values in between 0 and 1. In a similar way, 10/7 would lie between 1 and 2. 29/13 would be between 2 and 3, and so on. So you probably call a number like 2/5 or 10/7 a fraction, as do I, as would almost everyone, I believe. And a fraction just means a fragment or part of something whole. The thing is, however, in proper fractions like 10/7, they're not fragments of something whole, because actually 10/7 is greater than 1. So it's something greater than a whole, but it's still going to be fragments of something. On the other hand, what we can do is we can make fractions make sense if we think of them as simply a ratio between themselves and one whole. So therefore, as a consequence, any fraction is simply the ratio of two whole numbers. So if we conceptualize it like this, it's actually rather powerful, and I'll give you some explanations and examples right now. So, some examples of what we've just been saying. 10/7 is a ratio of 1. So we can think of 10/7, like we've said, we can think of this in proper fraction as being a ratio of itself to one whole. So 10/7 is a ratio to 1. If you multiply both sides of a ratio by 7, that gives us 10 parts on one side and 7 parts on the other. 2/5 as a ratio to one whole is the same as 2 to 5, just multiplying both sides of this ratio by 5. So 2/5 you can think of as being 2 slices out of a whole, which would be 5 parts. So as a ratio, it's the same as saying for every 5 slices, we actually have 2 which exist. So if 5 is a whole, we've got 2 pieces out of the 5. So it's a ratio of how much we actually have versus what would make a whole unit. In general, algebraically, the ratio of a over b to 1, so thinking of a over b as a fraction, we can conceptualize it as a ratio in this form, which is the same as ratio of a to b. So ratios and fractions are inextricably linked, and you've probably noticed that from work at GCSE. So for this very reason, another name for a fraction, either proper or improper, is a rational number. Rational as in ratio. So is a rational number the same as a fraction? In most situations, yes, pretty much it is. Two fractions like 2/3 and 4/6, now they are different, they look different and are different. However, you should know that 4/6 would simplify down to 2/3. So although they're different, they are actually still equal. So they're equal or equivalent fractions. So another way of saying this, each of them represents the same rational number which would occupy the same point on a number line. In a sense, a rational number, the actual ratio that is, consists of a whole family of equivalent fractions. So we can write the same equal ratio in multiple different ways. So the set of all rational numbers is this double struck capital Q symbol. It's the set of all fractions defined as follows. So the rational numbers are such that a is an integer and b is an integer slash 0. So b is an integer excluding 0 is what this means. So a is an integer, b is a non-zero integer such that we have a over b, and that will always generate a rational number. Remember, b can't be 0 because if b were a 0, we can't divide by 0, hence we'll need this limitation on the value of b. So just saying the same thing there. b slash 0 means all integers without 0. So why Q? You might be thinking, why not R for rational? Well, R's already been taken for the real numbers. Q was assigned to denote the rationals in 1895 by Giuseppe Pino after quotiente, which is quotient in English. So what about the properties of the rational numbers? Well, it's closed under addition and multiplication, and here's why. So let A over b and c over d be different rational numbers so that a, b, c and d are all integers, but b and d aren't equal to 0. So just making sure these denominators are non-zero. Then addition, we'd have a over b plus c over d. Getting the denominators the same, we could cross multiply. So b times d would give us ad over bd, and d multiplied by b would give us bc over bd. So a common denominator of bd, and at the top would be ad plus bc. Now ad would be a multiplied by d, integer multiplied by an integer, which would be an integer. Integers are closed under multiplication, and similarly for bc, this would also be an integer. So if this is an integer plus another integer, which again would also be an integer because we've established integers are also closed under the property of addition. So if this is an integer and also the denominator is an integer, not equal to 0. So if we add two rational numbers, we have an integer on the top and a non-zero integer on the bottom. In other words, we have another rational number. So therefore ad plus bc over bd would still be rational, so it's closed under addition. Multiplication, similar really. A over b times c over d gives us a multiplied by c, and b times d gives bd. AC is an integer because, like I've said before, the integers are closed under multiplication, and similarly for bd. So this gives us another integer over another integer, which therefore is a definition of a rational number too. It's also, I'm not going to do it here, it's pretty straightforward to show that Q is also closed under subtraction by considering subtraction as the inverse of addition. So again, if we just did a over b minus c over d and got the denominators the same, it would drop out in much the same way. Okay, instead of a plus there, you'd have a negative here, but because the integers are closed under subtraction, you can make that conclusion yourself. Try it yourselves if you want to, and convince yourselves that Q, the rationals, are also closed under subtraction. So, irrational numbers and the real numbers. Final piece of the puzzle. The set of all natural numbers, which is a big double struck n, is contained in the set of all integers z, which is contained in the set of all rationals q. So the naturals encompass both the integers and the rationals. So paradoxically, all of these sets of numbers are countably infinite, which means that hypothetically you could list the elements and assign a natural number to each. Furthermore, any natural number or integer is also a rational number. So for example, 12 could be written as 12 over 1, or minus 5 could be written as minus 5 over 1. So any natural number or integer could be rewritten as a rational number. The easiest way of defining an irrational number would be to simply say it's a number that is not rational. It seems like a bit of a cheat, that, but irrationals can't be expressed as fractions. Another way to define an irrational number would be as a real number which is not rational. As a consequence, the set of all real numbers, capital double struck R, is a set of all rational and irrational numbers combined. A real number is a value of a continuous quantity that can represent a distance along a line. The adjective real in this context was introduced in the 17th century by Descartes. What's strange about real numbers is that it is the only set of numbers we have met so far to have a property akin to length. Real numbers can be thought of as points on an infinitely long line called the number line or the real line, where the points corresponding to integers are equally spaced out. Furthermore, the set of real numbers is uncountably infinite, unlike the rationals, integers and natural numbers, which means it could never be listed, even hypothetically. It could never be listed or assigned a list. Another strange property is that almost all real numbers are irrational. So even though we deal with rational numbers on a daily basis and the most familiar to us, almost all real numbers are actually the irrational ones, which is quite a thing to try and get your head around. Among irrational numbers, some you will know about, it's the ratio pi, which is a ratio of a circle's circumference to its diameter, Euler's number, which is given by lowercase e, the golden ratio, phi, and the square root of 2. In fact, all square roots of natural numbers, other than perfect squares, by perfect square I mean just a square number, are irrational. So irrationals can be approximated by rationals. So for example, 22/7 is very close to pi, but they can never be equal to irrationals. So a rational number can get close to irrationals, but it can never be the same thing. It wasn't actually until the 16th century that European scholars and mathematicians finally accepted negative rational and irrational numbers as existing and worthy of merit on the same scope of mathematics. So these numbers now, though, play an essential part in mathematics at all levels. So that was probably an awful lot to digest. So if you've got through all that without falling asleep, very good. And to make sure you have been kept on your toes, there are some suggested exercises here for you to try, which the previous stuff we've talked through should help you with. So you may have been okay just reading through the notes without watching the video, and if that's the case, then great. And my video is essentially just a colour commentary of the notes. If you need to rewind to refresh yourselves, that's absolutely fine and understandable. You can try these questions in any order. What I'd suggest you do would be to press pause now, jot them down if you've not got notes in front of you, and attempt them, then press play to see my video solutions of each one. So if you'd like to do that now, press pause and then press play to see the solutions. Okay, question 1. By rewriting a section of the sequence of natural numbers as appropriate algebraic representatives, show that the sequence of natural numbers can be presented in terms of multiples of 5 and non-multiples of 5. And it says here to write 15 consecutive natural numbers represented algebraically in this manner. So, multiples of 5. Well, a multiple of 5 has to be of the form 5n. So, I'm going to write here the first multiple of 5 as being 5n. So after 5n, the next number bigger than 5n, the next consecutive natural number after 5n, would be 5n plus 1. Then one bigger than 5n plus 1, we'd have 5n plus 2. After 5n plus 2, 5n plus 3, and now hopefully you get the idea. We then have 5n plus 4. And then we'd have 5n plus 5, but 5n plus 5 has a factor of 5 in the 5n and the 5. So the next one, we could factorise out the 5 and say it's 5 lots of n plus 1. So just by doing that, it makes it clearer that we're talking here about the next multiple of 5. So going on further, this is 5n plus 5. We then have 5n plus 6, 5n plus 7, 5n plus 8, 5n plus 9, and the next one would be 5n plus 10, but again this is a multiple of 5, so that can be written as 5, comma, n plus 2. So how many have we got so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we need an extra 4 to try. So the next one, this is 5m plus 10, therefore the next one will be 5m plus 11, then 5m plus 12. I've not had myself enough space here, which is quite annoying, so I'll try and squeeze it all on the same page. So 5m plus 11, 5m plus 12, 5m plus 13, and finally 5m plus 14. So as you can see here, what we'd actually have would be multiples of 5 as every fifth number along. There we go. So multiple of 5 for non-multiples of 5. If you divided these by 5, you'd have a remainder of 1, 2, 3, 4. Then here is a multiple of 5. So that's just an extension of what we saw earlier in the explanation of this subchapter. So that's question 1 done. This could be done in other ways, of course. For example, we could have started with something like 5n minus 4, 5n minus 3, 5n minus 2, 5n minus 1. So we could have started lower than 5n if we wanted, but I think it's easy to try and keep it to positive signs only. Just my preference, but not the only way of doing it. Question 2, Bernard here is saying that an irrational number multiplied by a different irrational number will always give an irrational number. Provide an example, either numeric or algebraic, to illustrate that Bernard is wrong. So let's go for numeric first. So, for example, the most obvious, I think, irrational number is root 2. That's the most famous one. And like I mentioned earlier in this chapter, any square root of a non-perfect square is always irrational. So as long as what we're square rooting isn't a square number in itself, we'll always get something which is irrational. So I'm going to pick as a next one the square root of 8. So if we just think about what we're doing for a minute, 2 isn't a square number, nor is 8. So that's going to be irrational. Root 8 is also irrational. But when we multiply these together, that'll give us the square root of 16. But we can square root 16. That would give us 4. So that disproves Bernard. So therefore we can say Bernard is wrong. Doing it algebraically, I'd suggest something like this might be the best thing. So just set out our stall and think of a number which is going to be not a square number. So for example, I'm going to pick the letter A. So let A be a natural number such that A is not a square number. Now we just need to contrive an example involving A such that A multiplied by something else would give us a rational number. So therefore we can say the square root of, we could just hijack this example here really, therefore the square root of 2A multiplied by the square root of 8A, because A isn't a square number, the square root of 2A would be irrational. So both of these are irrational. But if we multiply these two together, 2 times 8 gives us 16, so that gives us a square root of 16, and a times a gives us a squared. So this would give us the square root of 16a squared, which would be 4a, which again is rational. So therefore, going via the algebraic route, that would show us that Bernard is wrong as well. So just as valid, could be done algebraically. Question 3. Given that the natural number a is both a multiple of 2 and a multiple of 3, first of all write a as a multiple of true using an algebraic representative. So for part a multiple of 2, we could say let a equal, say, 2b, where b is some natural number. Part b, we would write a as a multiple of 3 using an algebraic representative. So if a is a multiple of 3, similar to part a, we could rewrite a as 3 times another natural number, not necessarily equal to b though. So this time I'm going to get let a equal to 3c, where c is a natural number 2. So hence, using answers from a and b, we're going to make a pair of simultaneous equations from these, and we're going to show algebraically that a is therefore a multiple of 6. So, for part C, we're going to have a equals 2b, and also a equals 3c. So the trick here, what we can do, is we can take the top equation and we can multiply this by 3. So if we times the top by 3 and multiply the bottom one by 2, what we get here is 3a equals 6b. And then multiplying the bottom one by 2, that will give us 2a equals 6c. Now, if we subtract one from the other, 3a take away 2a, that will leave us with just 1a, which is what we want to find all along. So 3a take away 2a gives us a, then we have 6b minus 6c. And now we can factorise out a 6 from both of these. Gives us 6 lots of b minus c, which is therefore a multiple of 6. Because b's a natural number and c's a natural number, b minus c will also be a natural number because b has to be greater than c. So for example, let's say a were 12, then b in this case would have to be 6 and c in this case would have to be 4. If we equate 2b as being equal to 3c, then b has to be 1.5c. So this is 6 multiplied by some natural number. So therefore what we've proven here, we've proven that a is a multiple of 6, but a is just a multiple of 2 and a multiple of 3. So therefore, if a natural number is a multiple of 2 and 3, it is also going to be a multiple of 6. And we've proven it. Question 4. One of these sets, A, B, C or D, does represent the set of all rational numbers Q, and the other 3 do not. So for part A, which of these, A, B, C or D, represents the set of all rational numbers Q? Well, I'll just start by saying what it actually is. That's going to be set B. Okay, so set B is the one we're wanting. So A is any integer, and B is any integer apart from 0. And it needs to be having this restriction of not 0, because obviously if we have B on the denominator, which is equal to 0, that invites an infinite extra subset of undefined numbers into the set, because obviously we cannot divide by 0. That's just one of the basic rules of maths. And so that's why set B meets all the criteria. So going through the others step by step for part B, set A isn't, because set A does not represent Q because of it saying B is any integer. Well, B being 0 would be an integer too, and so A doesn't have this necessary restriction which stops 0 being in there. So like I said earlier, this permits undefined values, which would therefore mean some A over B would not be integers. Some A over B would be undefined. So that would be all the integers plus many more, which would pollute, if you like, the set. Set C isn't. It doesn't represent Q because of this thing here, saying that A can be any real number. That would allow A to be any fraction or decimal or a rational number for the numerator, whereas a rational number must be a ratio of integers only. So A would have to be an integer only, not just any real number. So this definition here is too wide open. And finally, D. D doesn't represent Q. It almost does, but by saying A and B are both integers without being 0, that excludes A from being 0, which consequently therefore excludes 0 from the set. If A can't be 0, then 0 can't be within this set. However, 0 is a rational number. So set D is therefore an incomplete version of Q that is missing the element 0. So D is almost set Q, but with one important element missing. Because D doesn't include 0, D can never quite therefore be the set of all rational numbers. Finally, question 5. This is a good one to think, pair and share with. Talk it through with a neighbour and see if you can crack it. I totally forgive you if you didn't crack this one, and I do also forgive you if you had a Google of it. It's just to get you thinking, really. So provide an example of two irrational numbers, A and B, such that A to the power B is rational. So this is one way you either see it or you don't really. So the clue here is we're talking about powers. Okay, so my suggestion would be to let A equal root 2 to the power of root 2. So that's definitely irrational. Then the trick here would be to let B equal root 2. And if you do that, then A to the power B would be root 2 to the power of root 2, all to the power of root 2. But then obviously a power of a power means we multiply the powers together. So root 2 times root 2 is just 2. So that would give us root 2 squared, which would just be 2, which is obviously rational. So that's almost a trick, really. I do not imagine you'll ever get a question like that in an A-level paper. That's almost like a puzzle or quiz type question, a bit of a brain teaser. So I thought to include that there just for a bit of fun, just to get you thinking. So there are all the questions. Hope you found that a useful introduction to year 13. There'll be another 2 videos coming up, which should then give you a full grounding to be more confident in terms of tackling year 13 pure with increased confidence. So thank you very much for listening to that. Do consider subscribing, and you'll hear from me soon in the next upcoming video. Take care, and I'll see you all soon.